In the LSDV approach, we controlled for the individual and time-specific effects using the dummy variables and estimated the beta coefficients. However, in the fixed effects within model, we estimate the beta coefficients after eliminating the fixed effects instead of controlling for them. The fixed effects are obtained after the estimation of the beta coefficients. We will discuss the one-way and two-way within Estimator separately. We will illustrate how we can eliminate the individual and time-specific effects to estimate the beta coefficients and then estimate the fixed effects. In the one-way fixed effects model, we include either the individual specific effects or the time-specific effects, but not both. In most practical cases of one-way fixed effects, we include the individual specific effects because unobserved heterogeneity of units is usually more prominent. For instance, personality and characteristics of individuals is important in studying income and consumption behavior. Or, managerial ability of firms has to be accounted for when studying the productivity of firms. A one-way fixed effects within model with individual specific effects can be specified as shown here. In this equation, yit is the dependent and xit is the independent variable. The term μi represents the individual specific effects, which are time invariant but different across individuals. The term epsilon-it is the usual error term which is independently and identically distributed with mean 0 and sigma square epsilon variance. It is important to note here that we can only estimate alpha plus μi together. The individual specific effects, μi, cannot be estimated separately in this equation. As a result, we need to make some adjustments to this equation 1 if we want to estimate the beta, alpha and μi. First, we average the equation 1 over time to arrive at the equation 2 shown here. In panel data, averaging over time implies that we take the mean of each individual unit values across time as shown in the table. For example, suppose we have data on I individuals across 4 time periods. The first individual unit y1 has the values of 4, 5, 3 and 4 in the given 4 time periods. The average across time for y1 will be 4, which is simply the mean of all the values in different time periods. In this way, we take the average of all variables across time for each individual unit and is shown by equation 2. The alpha and individual specific effects, μi, will stay the same in this equation even after averaging across time. This is because they are time invariant and do not change with time. Next, we subtract equation 2 from equation 1 to obtain the equation 3 shown here. You will notice that the alpha and the individual specific effects have been eliminated from this equation. This happens because both equations 1 and 2 contain the alpha and μi. Hence, they are eliminated when we subtract one from the other. In equation 3, we have successfully eliminated the individual specific effects from the model. By applying OLS to this equation 3, we can estimate the beta coefficients in the model. Now that we have estimated the beta, we have to obtain the individual specific effects, μi. As mentioned earlier, we can only estimate alpha and μi together in equation 1 and cannot estimate them separately without introducing some restrictions. Let us apply the necessary restriction and estimate the alpha and μi. To accomplish this, we average the equation 1 across all observations. That is, we take the overall mean of all the variables in the equation. For instance, to estimate overall mean of y or y double bar, we will take the sum of variable y for all individual units and all time periods and divide it by the total number of observations. This way, we obtain the y double bar and x double bar in equation 4. The alpha stays the same because it is a constant. But, we do not have the overall average of individual specific effects, μi, in this equation. This is because we introduce a restriction that the sum of μi across individuals is 0. Since their sum is 0, μi are eliminated from this equation. This restriction serves to avoid the problem of perfect multicollinearity similar to the dummy variable trap in the LSDV approach. Using this equation 4, we can estimate the alpha cap as shown in equation 5. we can obtain alpha cap from this equation because we already know the values of y double bar and x double bar from equation 4 and we estimated the beta cap earlier from equation 3. Substituting the values of yi bar, alpha cap, beta cap and xi bar, we can estimate the individual specific effects μi as shown in equation 6. Hence, we have estimated the beta coefficients as well as the individual specific effects using the one-way fixed effects within Estimator. The beta coefficients obtained from the within model are the same as the coefficients estimated using the LSDV approach. The difference is that the within Estimator eliminates individual specific effects with time demeaning to estimate betas, whereas the LSDV model controls for the individual specific effects using the dummy variables. As the name suggests, we include both individual and time-specific effects in the two-way fixed effects within Estimator. We can specify the two-way fixed effects model as shown in equation 1 here. The yit and xit are dependent and independent variables respectively. The error epsilon it is the usual error term which is identically and independently distributed with mean 0 and variance sigma square epsilon. The term μi represents the individual specific effects similar to the term we used in the one-way effects model. The two-way effects include an additional term gamma t which accounts for the unobserved time-specific effects or heterogeneity. In the one-way effects earlier, we eliminated the individual specific effects to estimate the beta coefficient. Similarly in the two-way effects, we will eliminate both the individual and time-specific effects to estimate the beta. Then, we will obtain the alpha, individual and time-specific effects afterwards. First, we will average equation 1 across individuals to arrive at the equation 2 shown here. The constant alpha and time-specific effects gamma t stay the same because they are individual invariant, that is, they do not change across individuals. The variables yt bar and xt bar are simply the means of these variables taken across individuals as shown in the table. For example, suppose we have 4 individuals and t time periods in the panel data. The mean of all individuals in the first time period will be 3 because the values of y are 4, 2, 1 and 5. Hence, we estimate the average across individuals for each time period to obtain equation 2. Moreover, we also restrict the sum of individual specific effects to be 0 across all individuals. This restriction is similar to the one we imposed in the one-way effects model. It helps to avoid perfect multicollinearity and estimate the individual specific effects later. Next, we average the equation 1 over time. We also performed this step in the one-way effects model. The variables y and x are averaged over time. The constant alpha and individual specific effects μi stay the same because they are time invariant or do not change over time. We also impose another restriction in this equation. We restrict the sum of time-specific effects to be 0. The logic behind this restriction is the same as before. It helps avoid perfect multicollinearity in the time-specific effects similar to avoiding the dummy variable trap in the LSDV model. Then, we average the equation 1 over all observations. We performed this step in the one-way effects model as well. The variables y double bar and x double bar have been averaged across all individual units and over all time periods. We also impose the same restrictions in this equation where the sum of individual specific effects is 0 and the sum of time-specific effects is 0. When we subtract equation 2 and 3 and add equation 4 to equation 1, we arrive at the equation 5 shown here. You will notice that the individual specific effects μi, the time-specific effects gamma t and alpha have been eliminated from this equation. Therefore, we can apply OLS to equation 5 and estimate the coefficient beta. After estimating the beta, we can obtain alpha cap in the same way as we did in the one-way model. The constant alpha cap can, therefore, be estimated by plugging in the estimated beta cap coefficients using the equation 6 as shown here. Furthermore, the individual specific effects as well as the time-specific effects are obtained with the help of the estimated beta cap coefficients as shown in the equations 7 and 8. we have all information on the beta cap, yi bar, xi bar, and the overall means of y and x in equation 7, and we can estimate mu I from these. Similarly, we already have all information on beta cap, yt bar, xt bar, and overall means of y and x, which can be used to estimate the time-specific effects gamma t. Hence, we have estimated the beta coefficients as well as the individual and time-specific effects using the two-way fixed effects within Estimator. The estimated beta coefficients will again be the same as the beta coefficients of the LSDV approach with individual and time dummies. We will further discuss the real-world application and interpretation of these models in the upcoming tutorials. The fixed effects within Estimator shares a similar disadvantage to the LSDV approach. Suppose we are estimating a one-way within model with individual specific effects. This model will be similar to the LSDV approach with individual specific dummy variables. In such a model, we cannot include time-invariant independent variables such as gender, race, and others. In the LSDV approach, effects of these time-invariant variables are absorbed by the individual specific dummy variables. In the within model, the effects of these time-invariant variables are eliminated while time-demeaning when we eliminate the individual specific fixed effects. As a result, we cannot include time-invariant independent variables in the model. Hence, if we are specifically interested in analyzing the effects of time-invariant variables, then we cannot use the fixed effects LSDV or within models. Similarly, if we are estimating the two-way model or LSDV with both individual and time-specific dummies, then we cannot include time-invariant or individual-invariant independent variables. The effects of time-invariant as well as individual-invariant variables are absorbed by the dummies in LSDV model and eliminated by the demeaning procedures of the two-way within Estimator. However, the within Estimator has an advantage over the LSDV approach that it does not consume additional degrees of freedom. When estimating the beta coefficients, the one-way and two-way within models simply eliminate the individual and time-specific heterogeneity. Therefore, we do not estimate additional coefficients like we did with the dummy variables in the LSDV approach. If we have too many individual units or time periods, the LSDV model may not estimate because of too many coefficients and loss of degrees of freedom. But, the within Estimator does not have this problem because it does not include any additional coefficients. Thank you for watching, and I will see you in the next tutorial.